Well, welcome back, statistics scholars. Our first topic for this section of the class is Anova, otherwise known as the analysis of variance. It's actually what Anova stands for. The AN for analysis, and then O for of, and then V for variance. And that's exactly what we're going to do. You may have thought to yourself as you were completing Lab 3, oh my gosh, this is so much work. And I bet, and it was, to be fair, because I had you calculate the standard deviation, the variances, take the square root to get the standard deviation. I had you calculate them 1, 2, 3 different times. So it was, kind of a lot of work. But I did that to refresh our memories about how to calculate the variance. Because an ANOVA is an inferential test statistic that we're going to use to be able to ask and answer a research question that uses the variance. We're going to calculate multiple different types of variances to get at our inferential test statistic that we're going to use to reject or fail to reject a null hypothesis. And this is just a poem here on the first slide written by Hugh Foley, an ode to the analysis of variance. And I think it's pretty funny, but then I would because I'm a stats geek. So, what is an ANOVA for? Good question. Glad you asked. Essentially, if you think about the 4 different inferential tests that we've learned to do, the one sample z-test, the one sample t-test, the independent samples t-test, and the paired samples t-test, we were really only comparing 2 numbers, right? In the one sample test, we had one sample that we compared to a known population average. In the independent samples test, we had 2 samples we were comparing to each other, an X bar to an X bar. In the paired samples t-test, we were comparing a D bar to a null hypothesis D bar, or a null hypothesis average difference. So we were comparing only 2 numbers. So we really only had 2 different groups as a maximum, right? In the independent samples t-test, we had 2 groups. So let's start with the independent samples t-test. We had 2 averages, and we wanted to ask if they were the same or different. So we did an independent samples t-test. But the world doesn't fit neatly into 2 groups all the time. Or as a researcher, you may want to do an analysis where you're comparing the averages of more than 2 groups. Let's take a quick example. Like, let's say you're a medical researcher and you're comparing the success rates of various birth control methodologies, right? Are there only two types of birth control? Nope. There's lots and lots. And what if you wanted to look at the averages between these multiple groups, like the average complication rate or the average, risk of pregnancy, right? With an independent samples t-test, you could only compare 2 averages for 2 groups. And what if you want to compare 3 groups or 4 groups or 5 groups or 6 groups or however many groups you want? Or here's another example. Let's say you're comparing a new depression drug, right? A brand new drug that's been developed to treat depression. And you want to compare that to an old drug. But then you also want to compare that to a placebo. Well, now you've got 3 groups. And how are you going to compare the average depression among 3 groups? Because you can't just do a t-test. If you look at the equation for a t-test, you got the effect in the top where you compare one mean difference to a null hypothesis mean difference. Remember that? But we can't just shove another X bar in there. That doesn't even make sense. What would you do? Go X bar minus X bar minus X bar? Nope. That doesn't make sense. So we need to do what's called an analysis of variance instead. It's a single inferential test statistic that you can calculate that allows you to decide whether or not there are any differences among as many averages as you care to look at. 3 averages, 4 averages, right? Like the average depression among 3 different groups of people, each of whom got three different types of drugs. The placebo, Zoloft, an old drug, and let's say a new drug for depression, right? And so there are some vocab terms I want you to know. In the world of ANOVA, so that's what the purpose of ANOVA is, right? Is to compare the averages of 3 or more groups. That is the purpose of ANOVA. But there's some new vocab words I want you to know. In the world of ANOVA, there's going to be a categorical variable because we have groups, right? We're going to have to be keeping track of a qualitative difference in our test participants. So let's use that drug example. You're going to have 3 groups where how they're different is what drug that they took, right? That's the qualitative or categorical variable on which they differ. Which drug did you get? The drug group is that variable, that qualitative variable. Well, we give qualitative variables, categorical group-based variables. We give it a new name in the world of ANOVA. We call it a factor. We call it a factor because we're asking this question. Does this qualitative categorical variable factor in and influence some other quantitative dimension-based variable? So if we're thinking about 3 different drug groups and how that impacts depression, we're wondering if the drug that you take factors in and influences your depression or influence these groups' depression. And then we talk about each of the different groups as being a particular level on that factor. So if I have 3 different groups for the single categorical variable, I have 1 categorical variable. Which drug did you take? Within that categorical variable, I have 3 groups. Well, that means I have 3 levels of that categorical variable. Now, sometimes in ANOVA, things get complicated, where you actually have more than 2 categorical variables. That is called a factorial ANOVA. We're not going to do those as a part of our class, but you should know that you can do them. And then every single unique group somebody is in is called a cell or a condition. I just want you to know that as just a vocab word as you move on in ANOVA land. And so here are some examples of factors. Ethnicity. Ethnicity is a factor. There's more than 2 ethnicities. And so let's say you were tracking income by ethnicity, right? Because you're curious if, race or ethnicity factors in and influences somebody's yearly income, right? And let's say you tracked 6 different distinct ethnicities in a particular part of the world. Well, then that one factor of ethnicity has 6 different levels. Or how about you're in school? Let's say you're looking in high school. You've got freshmen, sophomores, juniors, and seniors. You've got and let's say you're looking at average study times. That's the quantitative variable. How many hours a week do you study? So you've got 1 categorical variable, you're in school, with 4 levels. Freshman, sophomore, junior, senior. And you're wondering if year in school factors in to people's study times. Or when you're doing an experiment, right? We call it experimental conditions, because I'm going to create a research scenario where 1 group of people gets a placebo, a second group of people gets a new drug, a third group of people get an old drug. In that scenario, I've got 3 groups, one categorical variable. What drug did you get? 3 different levels, new drug, old drug, placebo, right? And then that creates 3 levels. And I'm going to see if the drug you get factors in to your depression scores by comparing the averages of these 3 groups. And that is the overall of ANOVA. Now at this point, sometimes students ask, well, why can't I just do a bunch of t-tests? Okay, well, let's wrap our head around that first, right? Let me draw it out for you. Because let's use an example. Let's use that drug example. Let's say I have a new drug, an old drug, and a placebo. Right? Let's say I get an average for the new drug, an average depression score for the people who take the new drug. Then I get an average depression score for the people who take the old drug. And then I get an average depression score for the people that take the placebo. Well, technically, then I could do 3 different t-tests, right? And who remembers the equation for the t-test? It's x bar minus x bar minus the null hypothesis mean difference, which is just 0, divided by standard error, where you have pooled variance times 1 over baby n plus 1 over baby n. Take the square root of that, right? That's the independent samples t-test. So sometimes students ask, well, why don't I just do 3 different t-tests? If I want to see if these 3 groups are different, right? Why don't I just do 3 different t-tests where I compare the new drug group to the old drug group? T-test number 1. I compare the new drug group to the placebo group. T-test number 2. And finally, I compare the old drug group to the placebo group. But I certainly could do that, theoretically. Instead of doing one test that we call an Anova, in this example, I could do 3 different t-tests. That would tell me if there are any differences among all 3 of these averages. And with 3 different groups, I would then need to do 3 different t-tests. But how many t-tests would I have to do if I had 4 groups? Because a t-test will tell me whether or not the averages are different, right? So let's say I have 4 groups. I have a new drug group, I have an old drug group, I have a placebo group, and let's say I have another old drug for depression. So now I've got 4 different groups, each of whom have an average depression score, and each one had a different drug experience. And I want to know if there are any differences in depression among these 4 groups. Well, I could do a bunch of different t-tests. How many would I have to do to get all of the different possible comparisons? Well, I'd have to compare the first group to the second group, and then the first group to the third group, and then the first group to the fourth group, and then I would have to compare the second group to the third group, okay, and then I'm going to have to compare the second group to the fourth group, okay, and then I'm going to have to compare the third group to the fourth group. Oh my gosh. To get at all the possible comparisons, I'd have to do 6 different t-tests if I have 4 groups. Whoa, that's a lot of tests. And it is. And for every new group that you have, you're going to have to do that. You're going to have to do a whole lot more t-tests. If you have 5 groups, you're going to have to end up doing let's count how many you'd have to do if you have 5 groups, right? Let's say this is now, let's say this is not the drug example, whoops. Let's say this is ethnicity, right? And let's say I've tracked 5 different distinct ethnicities and I'm looking at income. How many different comparisons would I have to do? Well, I'd have to do at least 6, because that's how many I had to do with 4, right? But then I'm going to have to compare 5 to 1, 5 to 2, 5 to 3, 5 to 4. So I'm going to have to do an additional 4 tests. So now I'm doing 10 tests. Oh my goodness. Wow. That's just, now I'm going to do 10 different tests. So it starts to blow up and become exponential at that point, right? We're having to do more and more and more t-tests for every group that you add. And every time you do another t-test, that is another independent samples t-test. It's another null hypothesis significance test with its very own alpha, its very own likelihood of a type 1 error. And because you're doing lots and 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 lots of t-tests, every time you do another t-test, you have a 5% chance, if you use an alpha of 0.05, of committing a type 1 error. Because remember, that's what alpha is. Alpha is your probability of committing a type 1 error. And so now, if you're doing, let's say you have 5 groups and you're doing, 10 different t-tests, right? Let's say you have 3 groups and you're doing 3 different t-tests. You've got 4 groups, you're doing 6 different t-tests, right? Every time you do another test, that test has a 5% chance. Well, then now we have to ask the question, what is the probability of committing a type 1 error at least once? Well, it's going to be, and this is an or question. Think about it this way. Remember back to probability, where I wanted to know what's the probability of having an orange backpack or a red backpack. And then I could just add the probabilities together. Or remember when I said what's the probability of being a man or being white? First, I added the probabilities together. Then I subtracted out the joint probability because being a man and being white were not mutually exclusive. Well, it's the exact same problem. It's the exact same problem here. Every single t-test has a 5% chance, an alpha of 0.05, of committing a type 1 error. That's why alpha is called the type 1 error rate. It's the probability that you're going to reject the null even if the null is true. And so if, let's say you only do 3 t-tests, that's it. All you're doing is 3 t-tests because you have 3 groups, right? So let's say we have just 3 groups, right? Let's use that drug example again. You've got a new drug, an old drug, and a placebo. You just have 3 groups. And you decide to do t-test number 1. Compare the old drug to the new drug group. Alpha is 0.05 for that test. Then you compare the old drug to the placebo. And you compare, that's alpha is 0.05 for that test. Then you compare the new drug to the placebo, right? Now you have another test with an alpha of 0.05. What is the probability of committing a type 1 error at least once? Well, what you're really asking is what's the probability of committing a type 1 error in test 1 or in test 2 or in test 3? And what do we know about OR questions from probability? You add the probabilities together. So it's 0.05 plus 0.05 plus 0.05, and then you subtract out that little joint probability because they're not mutually exclusive. But I've gone ahead and calculated it for you. The probability of committing a type 1 error at least once, if you do 3 different t-tests, is 0.14. So now your alpha isn't 0.05 anymore, it's 0.14. You have a 14% chance of committing a type 1 error at least once if you do 3 different t-tests. This is called inflated type 1 error. You're inflating it like a balloon. You're making it bigger. There's a much greater likelihood of it committing a type 1 error at least once if you have multiple tests. And so that's a problem. We don't want inflated type 1 error. We don't want to be committing type 1 errors. That's a bad thing. And so we don't want an alpha of 0.14 because we're doing multiple tests. And that's only with 3, right? Imagine what it would be if you're doing 10 tests. And imagine what you would be if it was doing 20 tests. Oh my gosh, you'd get super big inflated type 1 error, right? And so the F-test allows you to have one test, just one, where you can put all of your averages in a bucket and say, I have 3 different averages. Are there any differences here among any of these averages with one test? And the statistic that you calculate when you do an Anova is called an F-test. You calculate an F-statistic as a part of the F-test when you do an analysis of variance. And then that one test statistic, that one inferential test statistic called the F from the Anova will allow you to figure out whether or not you should reject or fail to reject the null, right? Where the null always says that things are going to be the same and the alternative always says that things are going to be different, right? So none of that has changed. And so why do we do the F-test? Why don't we just do a bunch of t-tests? Inflated type 1 error. Your true, what's called family-wise error rate, right? When you look at your family of analyses, if you do a bunch of t-tests, we treat all the t-tests as a family of t-tests. And we say the real alpha here is not 0.05 anymore because you're doing a bunch of tests. And that's a problem, inflated type 1 error. And so you do the F-tests to get around to have one test with one true alpha of 0.05 that then you can conduct to decide if there are any differences among your averages. Now, I want to walk you through a comic that sort of illustrates this idea about the problematic nature of inflated type 1 error. And this is from my favorite webcomic, XKCD, Randall Monroe. And here he says, jelly beans cause acne. Scientists investigate. And scientists are busy playing Minecraft, which I empathize with, right? And so the scientists did do a t-test, right? They grabbed two groups of people. They give half of them jelly beans, and the other half they give a placebo. Compare their average acne rates, the X bar for acne for the people who got jelly beans, and the X bar for acne from the people who got the placebo. Compare, and they go, nope, P greater than 0.05, no differences between these groups. Nope, no average differences at all between those who eat the jelly beans and those who don't, right? So they're like, okay, yeah, failed to reject the null. No, acne is not linked to jelly bean intake. And so they're like, that settles that. But then somebody has a bright idea and says, well, I hear it's only certain colors of jelly beans that cause it. And so they do a bunch of different t-tests. They compare people who eat purple jelly beans to a placebo. And then they find no results. Failed to reject the null, P greater than 0.05. Right? Because they find no link between purple jelly beans and acne. Then they find no link between brown jelly beans and acne. And then they find no link between pink jelly beans and acne. And then they do blue jelly beans and teal jelly beans and salmon jelly beans and red jelly beans and turquoise and magenta and yellow and gray and tan and cyan. And they're always finding this pattern of, look, these jelly beans are not any different. People eating these jelly beans, people who eat gray, salmon, red, turquoise, people who eat these jelly beans, these colors of jelly beans, have no greater or less acne than the people who eat a placebo. But then something weird happens, right? Well, we seem to find a link between eating green jelly beans and acne, P less than 0.05. Wait, what? But they find this weird link, right? And so then they do it with mauve, and there's no link in beige, and there's no link in lilac, and there's no link in black, and there's no link in peach and orange. So what is this? Do green jelly beans really cause an increase in acne? No, this is a type 1 error, right? If you do 20 different tests, and the null is true each and every single time, acne is not influenced at all by jelly beans. The null is true, right? There'd be no average differences between people who eat jelly beans and people who don't in terms of their acne if we could get at the population. But if we do 20 different tests and the null is true each and every single time, if we use an alpha of 0.05, 5% of the time you're going to reject the null anyway and commit a type 1 error. Well, what is 5% of 20? It's 1. And that's exactly what we saw in this data. One time out of 20, they found a weird link. They found a type 1 error. This is just a weird sample. They happened to grab weird people who had a slightly higher amount of acne, and they happened to give them green jelly beans. This is just chance. This is just a chance result. Green jelly beans have nothing to do with acne. This is a type 1 error. And I think a really great real-world example of this is research on autism and vaccines. There have been literally thousands of studies on autism and vaccines, thousands and thousands and thousands, finding no link at all between vaccines and autism rates. They've done large-scale epidemiological studies in the UK, and not just UK, all of Europe, right, in Denmark, where they actually look at like hundreds of thousands of people, no link between vaccines and autism, right? They compare people who get vaccines to people who don't. And what they find is people who get vaccines and people who don't have the exact same amount of risk of having autism. Over and over and over again, you see this. But then every once in a while, there's this weird study that seems to find a link. But what is it? That's a type 1 error. Samples are going to be different, right? In a sampling distribution, you're going to get some extreme samples just by chance. And so when you find these weird studies out there, these handful of studies that seem to find a link between vaccines and autism, those are just type 1 errors. That's what you'd expect to see in science if there is no link. Because sometimes you're just going to get weird samples, type 1 errors, right? Way over 95% of all the studies show no link between vaccines and autism. This tiny little handful of studies that seems to find a link, those are just type 1 errors. And that's why it's important in science to do replications, right? Because because in this example with the green jelly beans, because they're finding that green jelly beans seem to be linked to acne is probably just a type 1 error. If they redid the study, they would again find no link. That's why replication is important and why you have to look at the pattern of studies over time. One study is not enough to establish anything because there's always that probability that you're committing a type 1 error, which is why you replicate and you replicate and you replicate. Because this is what happens, right? On this slide, I know this is a type 1 error, but now a reporter who might be in the lab go, what? Green jelly beans are linked to acne. Oh, wow, they did a 95% confidence interval. That means we're 95% confident that this is real. And no, this is a type 1 error. It's a type 1 error, which is why it's so important to be informed about research and about statistics, right? Again, I think a less funny and more real-world example of that is the research on vaccines and autism, which is overwhelmingly clear there's no link between getting a vaccine and autism rates. But these handful of studies are exactly what you'd expect, given the fact that most alphas are 0.05. So, when you do an analysis of variance, you're going to be calculating a test statistic, an inferential test statistic, just like we did before when we calculated a z-statistic and then a t-statistic. Now we're going to be calculating an F-statistic. And just like we could put our z-statistic on a sampling distribution of z's, and that became a z-distribution, and we could put our t-statistic on a sampling distribution of the mean, and that became a t-distribution. The same thing is true for the F-statistic. It exists on an infinite number of samples and F's, called an F distribution. It's a sampling distribution of F statistics. And much like the T, that has a slightly different shape, right? So thus that we call it the family of T's, right? We talk about the family of sampling distributions for t-tests, where the shape changes very slightly and becomes more and more and more normal as degrees of freedom go up, right? That's why you have to look up the critical values in table A2 in the back of your book, right? You have to look those critical values up, and you have to know how many degrees of freedom you have in order to find the accurate critical value. Well, the same thing is going to be true with the F distribution, right? The sampling distribution when you're doing an F statistic. It's going to be a slightly different shape depending on degrees of freedom. But now there's going to be two different degrees of freedom that we have to worry about. There's going to be the kind of degrees of freedom that we did before, where we had to keep track of the number of people that we had, right? In a sample t-test, independent samples t-test, it was n-1 or n-2. There's going to be a very similar type of degrees of freedom for the Anova. We're also going to be keeping track of the number of groups that we have. 2 groups, well, you would do a t-test, so 3 groups, 4 groups, 5 groups, because depending on how many people you have, and depending on how many groups you have, the sampling distribution of F statistics is going to be a different shape. And here I have some examples for you of the different shape Fs. And notice that they're very skewed. They're very, very positively skewed. We no longer have things that are even remotely normal. They're not even sort of normal. They're very, very positively skewed. And an F distribution pretty much always will be. And the reason why that is because when we go through the math of an Anova, we're going to be basically dividing one variance by another. And since variances can never be negative because you square, you're never going to have a negative F. And because you can never have a negative F, you end up sort of chopping off the distribution at 0, right? And so you end up with something that is positively skewed. But the reason I teach you about the F distributions is because I want to keep in mind this is just like a Z or T test where there is this theoretical hypothetical sampling distribution where your F will be, right? And then you're going to compare your F to a critical value that cuts off alpha. So let's draw that on here, right? So here, Alpha is 5% of the tail, so there's going to be a critical value that exists on this sampling distribution. Let's use a better color. Right? 5%, but now there's only one tail, right? Anova there's no one or two tailed Anovas. They're all, it's a non-directional test, just so you know. There isn't tails because you have many averages, 3 averages, 4 averages. You're not going to specify which one you think is higher or lower, but you're just going to sort of look at them as a group, right? But you're still going to have a critical value that's going to change depending on the shape of your sampling distribution. And then you're going to see where your test statistic is in relation to that critical value. And if what you calculate is bigger than the critical value, reject the null hypothesis. And if what you calculate is not bigger than the critical value, fail to reject the null hypothesis. None of that has changed. It's just now our sampling distributions are pretty funky. And so now we're going to be looking up a critical F in table A3. Not table A1 or 2 now, but we're going to be looking up a critical F in table A3 now. So speaking of null and alternative hypotheses, the null and alternative hypotheses for an F statistic are always exactly the same for every single F test. The null hypothesis always looks like this. H sub 0, that's the null, is that in the population, the mean for the first group is equal to the mean of the second group, is the same as all of the other averages. So essentially, the null hypothesis in an F test says all of the averages, no matter how many you have, let's say G is the number of groups you have, 3 groups, 4 groups, 5 groups, however many groups you have, the null says all of your group averages are exactly the same. And that's why we have this symbology here. Mu1 is equal to mu2 is equal to however many averages you have all the way to mu sub g, which is just a symbol that indicates you can have as many averages as you want, and the null will say that they're all exactly the same. The alternative hypothesis is the mutually exclusive, collectively exhaustive opposite of that. And if the null is that they're all exactly the same, then the mutually exclusive, collectively exhaustive opposite is that at least one group is different from one other group. Not that they're all different from each other, not that 2 are different from each other, not that one group is different from all the others, but rather that when you look at all of your groups collectively, at least one group, let's call it G sub 1, let's call it mu sub G1, the average for any one of your groups is going to be different from the average of at least one other group. That somewhere among your averages, there's one mean difference that is statistically significant. That one mean is different from at least one other mean. That one pair of averages is different from each other. That is what the alternative hypothesis is. At least one group is different from at least one other group. There's at least one mean difference among your groups. So that's nice. The null and alternative hypotheses are always exactly the same for every ANOVA forever. So let's do a research example. So here we have, do freshmen, sophomore, juniors, and seniors in high school have different average study times? Well, the null hypothesis would be that the average study times for freshmen is exactly the same as the average study times from sophomores, which is exactly the same as the average study times for juniors, which is exactly the same as the average study times for seniors. That all 4 groups have precisely the same amount of average study times, that there's no differences among these averages. And the alternative is just that at least one group average is different from at least one other group average. That there's at least one mean difference here. It could be that the freshmen are different from the seniors. It could be that the sophomores are different from the juniors, or any pair. Seniors are different from the juniors, freshmen are different than the sophomores, who knows? Or they could all be. But the alternative is just that at least one pair of means is different from each other. That is the null and alternative hypotheses. So how am I going to get this F statistic, right? Now that we've set up the rationale for it, now that we've sort of wrapped our head around what it is, how are we actually going to calculate it? Well, first, we'll just sort of recognize how it's going to be somewhat similar to what we've already done before, Z and T tests. Now, the calculation of an ANOVA is different than with a Z or T test. With a Z or T test, once you had your averages and your standard deviations and your variances, you could just sort of plug in the terms into the algebraic equation and you just solved. But an ANOVA is different. An ANOVA is sort of like an onion. It's got layers. You got to peel it away. And so first, let's see how it's similar to a Z or T test, and then we're going to sort of reverse engineer the F. But and even though it does seem long and tedious, really all we're going to be doing is calculating different types of variances. And we already know how to do that. And so even though it seems long and scary and a pain, in reality, it's something we already know how to do. We already know how to calculate a variance. We just have to learn how to calculate special types of variances for an ANOVA. So let's look at what we have already done before. When we calculated a Z or T test, the inferential test statistic was a mean difference on top and then standard error on the bottom. That was true for all four tests. So mean difference on top, x bar compared to mu, right? X bar compared to x bar. D bar compared to the mu sub d for the population, right? You're always having some mean difference on top, and you're always then dividing by standard error. So you had the effect on top and error on the bottom. Well, that's exactly what we're doing with the F tests. We're going to be calculating an inferential test statistic called the F-statistic, where we're going to get some effect, and we're going to divide that by error. And the bigger the top is compared to the bottom, the bigger the F-statistic will be, the more likely it will be that we'll reject the null hypothesis, right? And unfortunately, because we have more than two averages, to get at the effect, we can't just subtract the two means, right? We can't just take x bar minus x bar, right? We can't do that. And we don't have this nice simple equation to get at standard error because we have more than two groups. And so effect and error are just going to be a little more complicated. We're going to have to do some complicated stuff to get at our effect and error. So what are we going to do? We are going to analyze the variance. We're going to calculate a variance for the effect. And then we're going to calculate a variance for the error. And first, I just want to sort of have us wrap our head around what we're really doing here. Because in an ANOVA, the effect is going to be a variance. Remember what a variance is, right? We're trying to get variability around an average, right? That's why I had you calculate it a bunch of times on your last lab. The variance is a number that we calculate that indicates how spread out people are from each other, how different they are from each other. And we're going to calculate a special kind of variance called the effect. And it's called the between variance. And it's essentially asking this question. Let's use the study times and class example. We've got this categorical factor. Remember how we have a categorical variable that we call it a factor now. And we were wondering if this category of being a freshman, sophomore, junior, or senior, if that's factoring in, if that category is factoring in and affecting people's study times. So we're going to calculate a variance to see if people's study times are variable because of the group that they're in. So we're going to calculate a variance due to the effect. And we're going to do that by looking between the groups, which is why it's called the variance between. And like any variance, the first thing you're going to have to do is calculate sums of squares. So put that in the back of your head. We're going to calculate sums of squares for the between. That's our effect. And then we're going to calculate sums of squares for within. That's our error. But really, we're just calculating two different variances. The variability in study times because someone happens to be in a category, freshman, sophomore, junior, or senior. And then we're going to calculate a different variance called error variance, right? Where we look to see all the other things that could possibly affect study times. We're going to shove that into a variance called error. And we're going to put the effect on the top and the error on the bottom. And so the effect is called between because we have different groups and we're trying to see if group 1, freshmen, is different from group 2, sophomores, is different from group 3, juniors, is different from group 4, seniors. So we're going to be looking between the groups to see if the scores vary, to see if study times are varying because people are in 4 different groups. We're going to call that the effect. Then we're going to be calculating a different variance where we're going to be looking at people's study times to be affected by anything else at all. And so we're going to be then looking at variance for error, all the other things that could be influencing study times having nothing to do with being in a particular category, being in a particular group, like freshmen, sophomore, juniors, and seniors. Because there's lots of like random things that could affect somebody's study times, right? Like their parents are going to affect your study times, and your extracurricular activities are going to affect your study times. But I don't care about that as the researcher right now, so I simply shove that into what's called the error term, the error variance. And we're going to put the effect on the top, effect variance on top, and we're going to put error variance on the bottom to get our F statistic. And so our F is going to be a variance because people are in a particular category, variability in study times because people were either freshmen, sophomores, juniors, and seniors. And then we're going to compare that to the variance for other reasons. Call that error variance. Not because anyone did anything wrong, but just it gets shoved into that bottom part of the fraction, and we call it error variance. Because remember, people are going to vary. But the more people are different based on their group category, the less people are different because of other reasons, the larger the F will be. The bigger the difference between people based on category versus the differences between people based on other reasons, the bigger F will be. Basically, the bigger the top is compared to the bottom, the bigger F will be, because that's how division works. And so another term for the F statistic is often called the F ratio, because you're actually comparing. You're getting a ratio of effect variance on the top, category-based variance, and you have error variance on the bottom. And the bigger the top is compared to the bottom, the bigger the F ratio is. Bigger inferential test statistics mean reject the null hypothesis, right? The bigger category-based variances compared to error variance, the bigger F will be, and you'll reject the null hypothesis and say somewhere among these averages, the groups are different. So, how am I actually going to get at these variances? So glad you asked. Well, first of all, we're going to give the variance a new name. And I'm going to go ahead and draw for you for just a second. So let's refresh our memory of how you calculate a variance in general. Not the special kind of variance that we're going to learn to calculate for an Anova, but just a variance in general. You took a person's score, you subtracted the average, you subtracted the grand mean, right? This is somebody's score, right? And you subtracted the grand mean. I talked about how we only started having to deal with subgroup averages after we had more than one group, but now we're going back to one sample land. I've got a bunch of people, and I just want to calculate the variance for this one group of people. I'm going to take each person, and I'm going to subtract the average for the entire group. Then I'm going to square those deviation scores, right? Then I'm going to add up those square deviation scores to get the sum of squares. Remember how this, before you do any division, what you've calculated at this point is called the sum of squares, because you're summing a bunch of squares, right? And then I divided by n minus 1, and that gave me my variance. Now, if I took the square root of it, I would have the standard deviation, but it's not called analysis of standard deviation. It's called analysis of variance. So first, let's remember that this is the equation for the variance. We all with me? Hopefully we are. Well, if we notice, this is an average. Remember how that was on the first test? Where I made you memorize that the variance was an average, that it was a mean. Remember the kidney bean? Well, the variance is a mean, is an average. What is it a mean of? Well, it's the average of the squared deviation scores. That's what it is. It's the mean of some squares. So the general total variance, when we were dealing in one sample land, long before we got to inferential test land, inferential testing, just the regular variance for a single sample gets this special symbol, and we call that the variance. But once we move into Anova land, once we now are going to give the variance a new name. We're going to be calculating variances. That's what they are. But we don't want to use the same name that we used for this symbol. We don't want to call it variance subtype 1 and variance subtype 2. No, we're going to give it a new name. We're going to call it a mean square, right? Because it is a mean, right? Yes, it is. And it's a mean of a bunch of squares, right? So our new name for the variance is mean square. And here's my mean square. That is our new name for the variance. And if we're getting the total variance, it's the mean square total. It's the total amount of variance, the mean square. But then, in Anova land, we're going to calculate two different types of variances. So using our new vocab term, mean square, we're going to be calculating two different mean squares. We're going to be calculating a mean square for the effect and a mean square for the error. And we're going to call it between for the effect because we look between the groups because groups are different. And then we're going to look within for the error because we're going to be looking within the groups to see how the people are different from each other, even within a particular group, because then that means other things are influencing their outcomes. So we're going to calculate two variances, but we give it a new name. We're going to say mean square between for the effect, mean square within for the error, right? And so how do we get these mean squares, right? Because we wouldn't calculate it the exact same way as we calculate the variance for the total. Well, we actually are going to calculate them in a very similar way. To get the mean squares, which is our new name for the variances, we're going to start by getting a sums of squares and then dividing by degrees of freedom, exactly like we did here. We got a sum of squares on the top, and then we divided by n minus 1, which was the degrees of freedom. Remember, n minus 1 is the degrees of freedom when you're doing a single, you have one sample of people. N minus 1 is the degrees of freedom. And so even before, when we were doing a one sample, just calculate the standard deviation, calculate the variance, we took sums of squares, and we divided by degrees of freedom. And that's exactly what we're going to do here too. We're going to take our sums of squares for the between, for the effect, and we're going to divide it by degrees of freedom for the between, for the effect. Then we're going to do the same thing for the error. We're going to calculate the mean square for the within, which is the error, by taking the sums of squares for the within and dividing it by the degrees of freedom within. Right? So it's the same basic form that we already knew before. First calculate the sums of squares, then divide by the degrees of freedom, and that will give you your mean square, which is our new name for the variance. Now, how are things going to be different now? Because I've already said, we are now going to be calculating two different types of variances. So it's not going to be calculated exactly the same as when we were calculating the total variance. Because now we're going to be basically taking the variance and carving it up. We're going to be saying this is the variance due to group category, and this is the variance due to error. We're actually taking this one variance and carving it up into two camps. Variance due to group category, like are you a freshman, sophomore, junior, and senior? And variance in study times due to everything else. Call that error. And so the sums of squares are going to look a little different depending on whether or not you're looking between for the effect or within for the error. And here are those sums of squares. Whoa, those are a lot of numbers. Don't panic yet. This down here is just the sums of squares total. This is actually the exact same thing as I've written here. I'll go ahead and circle that for you in orange. This is each person subtract the grand mean, right? Well, I'm just reminding you of that here too. Here is each individual person, x, subtract the grand mean, square its summit. That is the SS total. That is the total sums of squares, right? But we're going to be carving this up. Now, why does it have an IJ here? Well, because in Anova land, we have an individual human person, I, who is in just one group, J. So you take every single person and subtract the grand mean. Then if you squared those and added those up, you would have the total sums of squares, which we've already calculated a bunch of times. Every time you calculated a variance, you started out by calculating the sums of squares total. We just didn't call it sums of squares total because we weren't going to be carving it up into anything, right? And so now let's look above it. Take a deep breath. It's not as scary as it looks. So here at the top, we have our brand new sums of squares between. And here's how, and it's a type of variance. It's category-based variance, where we're going to be looking between the groups to see if the groups are different from each other. And so to calculate it, you take every single individual subgroup average. Each x bar is a subgroup average. So you take every single x bar and you subtract the grand mean. You're seeing how each group, on average, like the average study times, is different from everybody, the grand mean. I'm freshman. What is our average study times? Compare that to the grand mean. We're sophomores. Let's see how we compare to the grand mean. And the bigger the differences are among all three of your groups or four of your groups, the bigger this will be. The more variability there will be due to group category, the bigger the differences are between your x bars. So take every group average and subtract the grand mean. Then you're going to square those so they don't just sum to 0. Then you're going to add those up, where you start at the first group, I sub 1, and you go to the last group, where G stands for the total number of groups that you have. If you have 4 groups, start at the first group, go to the fourth group, do all the groups. And then as a last step, you multiply by baby group sample size, because you have to amplify your effect by how many people it's based on. So let's say there are 5 people. You have 5 freshmen, 5 sophomores, 5 juniors, and 5 seniors. Then you would multiply it by baby n, right? And we're going to keep things simple, and we're going to just deal with ANOVAs where there are the exact same number of people in all of your groups. It just keeps things cleaner. You don't have to do an ANOVA where all the groups are the same size, have the same number of people in it, but we're just going to deal with that because it's just easier. So we don't have to learn a bunch of different equations. So this is the sums of squares between, where as a last step, after you subtract the subgroup average, subtract the grand mean from it, you're going to square those, then you're going to add those up, then you're going to multiply the whole thing by baby n, which is your individual group sample sizes, where we are going to assume that all the groups have the exact same number of people in them. That will give you your sums of squares between. Now you're going to get your sums of squares within, which is for your error. And here you take every single individual person and you compare that person to their own subgroup average, because now you're looking within the group. You're looking within the group to see if each person within one group is different from that average. So now let's say we're just talking about freshmen, and I'm a freshman, and now I'm being compared to my own freshman average. And I'm another freshman, and I'm being compared to my own freshman average. And then you'll do that for all of the different people. So you're going to have all the people, I sub j, x, I sub j just stands for individual person, I, individual, in just one group, j. And you then compare that to their own subgroup average. So you compare the freshmen to the freshman average, and then the sophomores to the sophomore average, and then the juniors to the junior average, and then the seniors to the senior average. Right? And I only include this one here to show you, you already know how to calculate this. These are just 2 different types of sums of squares. This is category-based sums of squares. How is each average different from the grand mean? So you're looking between the groups, x bar 1, x bar 2, x bar 3, x bar 4. How is each group different from the overall average, right? And then you're going to look within the groups. How is each one person, individual person, different from their own subgroup average? That's why they're called between and within, because that's where you're looking, within or between. It's between for the error, excuse me, it's between for the effect, and within for the error. And so this slide is just explaining to you in words exactly what these equations are telling you to do. Now, again, I only showed you the sums of squares total so that you could compare it to these other two new equations. It's only these two equations that you're going to need to calculate an F if you're doing it by hand. Also, because this is the total amount of variance and you're sort of carving it up, you need to know that if you take the sums of squares between and you add it to the sums of squares within, that'll actually give you the sums of squares total, right? So that's an important piece of information to know, that because you're just taking the total variance and carving it up. Here's the variance in study times because people are in a category, sums of squares between. Here is the sums of squares, the variance, because people, everything else, right, that's within. You're just carving up that variance into two camps. And so the first step is to calculate the two sums of squares. And all this slide is to break down in words exactly what these equations are doing, right? And so here, the sums of squares between. Take each individual group average, x bar, subtract the grand mean. So if you have 4 groups, you're going to be doing that 4 times. X bar 1 minus the grand mean. X bar 2 minus the grand mean. X bar 3 minus the grand mean. And et cetera, right? Then you're going to square those after you've gotten the differences. Then you're going to add those up, and then you're going to multiply that summation by the individual baby group sample size. This is going to be the sum of the squared deviation scores for the group means compared to the grand mean. Like that's just the fancy definition of what's happening here. But you just have to know how to calculate it, right? Just take all the x bars, subtract the grand mean, square them, add them up, multiply by baby n. The sums of squares within is where you take each individual person's score and you subtract the individual subgroup average, the subgroup mean. Then you'll square those, then you'll sum those up. And now you have your sums of squares within. And the sums of squares total, you already know how to calculate. It's the same as it was before for when you were doing the variance. Each person's score, subtract the overall grand mean, square them, add them. Now you have the sums of squares. But we're not done. Because what do you have to divide the sums of squares by to get your mean square, to get your variance? The degrees of freedom. And degrees of freedom are going to be different for between versus within. When you're looking at between the groups, the degrees of freedom is the number of groups you have minus 1. That's your degrees of freedom between the groups, G minus 1, where G is the number of groups that you have. So in our example with freshmen, sophomores, juniors, and seniors, it would be 4 minus 1. So degrees of freedom between would be 3. So you would take your sums of squares between and you would divide by 3. Degrees of freedom within is going to be the total number of people that you have minus the number of groups that you have, right? The total number of x bars you're dealing with, which is the total number of groups. So n minus g. And let's say I had 5 people in each group, right? Well, my baby group sample size is 5 then. If I have 4 groups, that means I must have 20 people, right? Big N would be 20 then. So I would take 20 minus 4, and my degrees of freedom within would then be 16. And so I would take whatever the sums of squares within is and divide it by 16. And then degrees of freedom total is just n minus 1. And much like we were taking the sums of squares and carving them up into the effect and error between and within, which allowed us to say the sums of squares between plus the sums of squares within is just going to be the sums of squares total. It's the same thing with degrees of freedom. You're taking your total degrees of freedom, n minus 1, and carving it up into category-based degrees of freedom and error degrees of freedom. So degrees of freedom between plus degrees of freedom within is in fact going to be degrees of freedom total. That's just not something else you need to memorize. And now I can get my mean squares. My mean square between, SS between over degrees of freedom between, and my mean square within, SS within over degrees of freedom within. And so this then becomes how we report our F statistic and how we finally then calculate it. Now the ANOVA is just variations on a theme, no pun intended. right? It's just calculating different types of variances, which we already know how to calculate, but then putting them together and doing them the right steps to get the F statistics. I don't think it's more challenging than anything that we've done. It's just more tedious. It just takes more steps. It's just more like an onion. And like any good onion, sometimes it can make you cry. Sorry, those are the jokes, right? And so you report the F statistic like this. F, and then you report the degrees of freedom between, and then you report the degrees of freedom within. And then you take your mean square between, which is our new name for the variance for the effect, and we divide it by the mean square within, which is the variance for the error, right? And now we can get our F, right? This was a lot of numbers, wasn't it? Yeah, it was. Before we work through an example by hand, because I'm totally going to do that for you, we'll work through a quick example. I do want to say, yes, this was a lot of numbers, right? How are you ever going to keep them straight, right? Because first you're going to have to calculate the sums of squares, and then you're going to have to calculate the degrees of freedom, and then you're going to have to keep track of within versus between, and what's with, and your head's going to explode, right? So we also need to learn, in addition to just calculating the F, how to organize our F information. And this is what is called the source table. This is what is called the F table. And as you're calculating these things one at a time, you use a table like this to plug in the numbers to keep them straight. It is an invaluable tool. It is super important for keeping things organized when calculating an F statistic. Because again, none of the steps in calculating an F are super duper new. It's just variances and degrees of freedom, both of which we already know about. Sums of squares, degrees of freedom to get a variance. We're just putting them together in a new way. And so we have to learn how to keep things straight, right? And so here is an example of how you can use an F table. The nice thing about an F table is that because we know that between plus within always equals total, you can actually use a source table to like fill in the blanks sometimes, which is sort of nice, right? Especially if you already know like the total amount of sums of squares, you already know total degrees of freedom. Then if you calculate between, which is easier than calculating within, you can actually fill in the blanks. And watch me do this. Because I know between plus within always equals total, I can take 780, subtract 350 to find out what my sums of squares within is. Let's see, 780 minus. And so now I know that this is going to be 430, right? Because between sums of squares and within sums of squares is always going to be total sums of squares, right? The between plus the within is always going to be the total. And so then I can do the same thing here. Because I know that between plus within is going to be total, I know that I can just put this as 96, because 96 plus 3 is 99. I can also figure out other information from looking at this source table. Because I know degrees of freedom is G minus 1, I know that there must have been 4 groups, because degrees of freedom between is 3. G minus 1 is 3. There must have been 4 groups, because 4 minus 1 is 3. I know there must have been 100 people, because I know that the degrees of freedom within is going to be n minus g, or 100 minus 4. And so I know that degrees of freedom within is 96, so I know there were 4 groups, and I know there must have been 100 people. And now I can just divide across to get my mean squares, and then divide down to get my F. And then watch me do this. 350 divided by 3 is 116.66667. And 430 divided by 96 is 4.479. Now, so my mean square between is 116.667, and my mean square within is 4.479, 430 divided by 96. And now I can get my F by taking 116.667 and dividing by 4.479. And so then 116.667 divided by 4.479 is 26.048. And so that is my inferential test statistic. This is then my F statistic that then I will compare to a critical value. And if it's big, then I will say somewhere among these averages, there are differences, right? Now, and this is how you can then use a source table to fill in the numbers to organize your thinking. So, a couple of the things before we calculate one from start to finish is you can really think of an ANOVA as an extension of the independent samples t-test, because mathematically and conceptually it absolutely is. ANOVA was derived by a man named Fisher, which is actually why it's called an F-test, and it actually flows both mathematically as well as conceptually from the independent samples t-test. And because it's generalized, because now you can do more than 2 groups. ANOVA is like a t-test, but for 3, 4, 5, 6, 7, 8, 9, 10, or however many groups you want. So it is a literal extension of the independent samples t-test. And you should also know that there is what's called the repeated measures ANOVA, which is a mathematical and a conceptual extension of the paired samples t-test. We're not going to do those in here, although your book does talk about them, right? We're just going to focus on what's called the one-way between subjects ANOVA, which is where you have different independent groups, just like in an independent samples t-test, where you have one categorical variable. That's why it's called one way. We're going to focus on that one-way regular ANOVA with one categorical variable that has 3 or more groups, where you're comparing the averages of those 3 groups. But because it's an extension of the independent samples t-test, it has the exact same assumptions: normality of the populations, homogeny of variance in the populations among all of your groups, and that all of your people are completely independent, right? Those are the exact same assumptions from the independent. Those are the exact same assumptions from the independent samples t-test, right? So yeah, because ANOVA is just an extension of that exact same type of question you're asking, it's got the same assumptions. And here is my handy dandy formula slide where all of the different relationships for ANOVA are summarized. That to get the F-test, you essentially are going to have to get a mean square between the groups for your effect, a mean square within the groups for your error. To get the mean squares, you need to take your sums of squares and divide by degrees of freedom. Here's how you get the sums of squares between. Take each subgroup average, subtract the grand mean, square it, add it, multiply by n, baby n, not big N, baby n. To get the sums of squares within, you take each individual person, subtract the subgroup average, square those, add those up. Well, now you have the sums of squares that can be plugged in here, and the sums of squares within that can be plugged in here. Then you get your degrees of freedom between by taking g minus 1, the number of groups minus 1, plug it in here. Then you get your degrees of freedom within, n minus g, and you plug it in here. And I've only given you the sums of squares total and the degrees of freedom total to remind you that this is really similar to things we've already done before. And I also want to remind you that total is always going to be between plus within, which is why sometimes then we can use that source table, that ANOVA table, to organize our numbers. Sometimes we can fill in an incomplete one and get around calculating sums of squares at all if someone is nice enough to give us an incomplete ANOVA table, right? Just like I did in this example here, right? Wasn't that awesome where I was able to just fill in the numbers without actually having to calculate anything long by hand? Yeah, incomplete ANOVA tables might be in your future, right? So this is just a handy formula slide to remind you of all the things you need to know in order to do an ANOVA. But then at the end of the day, when you calculate an ANOVA, it's the same process when making a decision. You're going to calculate your F-statistic. You're going to go to the F table, A3, in the back of your book. You're going to use both of your degrees of freedom now. Degrees of freedom between, which is called the numerator degrees of freedom, right? Because it's in the numerator of the F-stat, right? Between is in the numerator, within is in the denominator, right? So you take your degrees of freedom for the numerator, between, and you take your degrees of freedom within for the denominator, choose an alpha, and then you'll be able to find a critical F. Right? And so then if what you calculate is bigger than the critical value, reject the null hypothesis. So here's an example, right? Here I have degrees of freedom between is 2, and here I have degrees of freedom within is 15. That means I must have had 3 groups, and I must have had 18 people, right? Because G minus 1 is 2, so 3 minus 1 is 2. And N minus G would be 15. And so N would be 18 minus 3 groups is 15. And let's say I choose an alpha of 0.01. Well, then my critical value would be 6.36. That would be the critical value on this F distribution. And so if I calculate something bigger than 6.36, reject the null hypothesis. Now, why did I choose an alpha of 0.01? I don't know. I get to pick it. I just want to remind you, you don't always have to pick an alpha of 0.05. If I did pick an alpha of 0.05, right, it'd be much more, it'd be in here, and my critical value would be much smaller because I'd be allowing 5% to be in the tail, right? All of that stuff about sampling distributions, alpha, all that stuff is still here. It's just in a different type of research situation. So, test time. If you get a big F statistic, bigger than what? Bigger than the critical value, then it means you're going to have calculated something with all of those steps that was bigger than the critical value. That means P is going to be small. That means you're going to reject the null hypothesis. That means you're going to say there is a difference somewhere among your groups. Now, you don't know which groups are different from each other. You don't know how different they are, but you know at least 2 of them are different from each other, right? So let's work through an actual example using this example. Let's make up, let me give you some data, and we'll work through an example from start to finish. So now here I have some data, right? So let's see what we already know. And let's keep track of what we already know as we know it. And then we'll keep track of it in our source table. All right, so the first thing that we notice is that we have 4 groups, right? And so let's already fill in our degrees of freedom between, right? Let's just go ahead and fill that into this source table. Our degrees of freedom between is going to be 3, because degrees of freedom within is the number of groups you have minus 1. And we also can see that we have baby n is 5, because there's 1, 2, 3, 4, 5 people in the first group. Oh, whoops, I forgot to change this name. Sophomore. Sorry. We have 1, 2, 3, 4, 5 people in the second group. 1, 2, 3, 4, 5 people in the third, and then 5 people in the fourth, right? And again, we're just going to keep things simple. And for our one-way ANOVAs, we're going to assume the same number of people in each group. And so now we have baby sample size is baby n is 5. So big mama n, big daddy n is going to be 20, because 5 times 4 is 20, right? And so now I also then know degrees of freedom within, because I'm going to take the total number of people, 20, and I'm going to subtract 4. So my degrees of freedom within is going to be 16, n minus g. All right, that's easy. But now I'm going to have to get my sum of squares, and that's where things get a little dicey. Because now, well, get a little like an onion, where you got to peel it and you got to keep track of things. So let's start out with our sums of squares between. And here is that equation for sums of squares between. Here it is. So here, what are we going to need? Well, we're going to need an average for each of the groups. We're going to need an average for freshmen, an average for sophomores, and an average for juniors, and an average for seniors. And then we're going to need an average for everybody. So first, let's do that. Let's get the averages for the 4 groups. All right, so when I add 5 plus 7 plus 6 plus 5 plus 9, I get 32. 32 divided by 5 is 6.4. So the average for the first group of freshmen is 6.4. And then as I move on to my second group, I take 1 plus 2 plus 4 plus 1 plus 3, and I get 11. 11 divided by 5 is 2.2. So my average for my second group, sophomores, is 2.2. And then for my third group, when I take 2 plus 3 plus 5 plus 3 plus 1, I get 14. 14 divided by 5 is 2.8. So the average for my third group is 2.8. And then for my last and final fourth group, when I take 8 plus 7 plus 4 plus 8 plus 6, I get 33. 33 divided by 5 is 6.6. And so now I have all of my X bar sub i's, all of my individual group averages. Well, now I'm going to need a grand mean, X bar sub grand. So I'm going to need that too. And so then when I take all of these numbers, add them all up and divide by 20 to get the grand mean, so 5 plus 7 plus 6 plus 5 plus 9 plus 1 plus 2 plus 4, all of these 20 numbers, when I add them all up and divide by 20, I get 4.5. So the grand mean is 4.5. And now I can do the steps that allow me to calculate the sums of squares between. So now when we look at this equation, the first step is to take each subgroup average and subtract the grand mean, which is exactly what I've done here. I've taken the average of freshmen, 6.4, and I've subtracted 4.5 to get 1.9. I've taken the average for the sophomore group, 2.2, subtracted the grand mean, 4.5 to get negative 2.3. I've taken for the juniors, 2.8 minus 4.5 to get negative 1.7. And I took for the last group, 6.6 minus 4.5 to get 2.1. So I've now done this step. My next step is to square these. And so now here, I've taken all of these subtractions, all of these deviations, and I've squared them. 1.9 squared is 3.61. Negative 2.3 squared is 5.29. Negative 1.7 squared is 2.89. 2.1 squared is 4.41. So now I've done this step. My next step is to add all these together, where I started the first group and I go to the last group G. So I'm going to take 3.61, I'm going to add it to 5.29, add that to 2.89, and add that to 4.41. And that's exactly what I've done here. The sum of these 3.61, 5.29, 2.89, and 4.41 is 16.2. And so my last step is to multiply this by 5, because that is the individual baby group sample size. And that is the last step. Right here is to multiply the 6.62 by 5, because that is the individual group sample size. I'm amplifying it by how many people were in each group. And that is 81. So my sums of squares between is 81. And so now I just put that on my source table. Voila! But now I'm going to need to calculate my sums of squares within. So I go back to my data, and here is my equation for the sums of squares within. I'm going to take each person and subtract their own subgroup average. So I'm going to take all the freshmen and subtract 6.4 from each of their scores. I'm going to take all the sophomores and I'm going to subtract 2.2 from all of their scores. Then I'm going to go to the juniors and subtract 2.8 from all of their scores. Then I'm going to go to the seniors and subtract 6.6 from all of their scores, because that's what this is telling me to do in here. Take each person's score within each group, IJ, individual person in just one group, and subtract the individual subgroup average from that score. So that's the first step. So that's what I'm going to do. Ta-da! And that's exactly what I've done here. I have taken each person's score, X sub ij, and subtracted their own individual subgroup average. Now, as you can see, calculating the sums of squares within is much more of a pain than calculating the sums of squares between, right? Within, you're having to look within each group, and so you're having to keep track of each individual person. In the sums of squares between, we got to look between each of the groups by looking at the X bars compared to the grand mean, and so that was just a whole lot easier, right? The sums of squares between is just easier than doing the sums of squares within. But this is what I've done, right? I've now done this first step, taken each score and subtracted the subgroup average. Now I'm going to have to square all these scores, because this is just like a variance, right? It's just the mean square, the variance within. So I'm going to have to square all these scores. And voila again, this is exactly what I've done. I have taken each of the deviation scores for the subgroup averages, and I've squared them all. I did that for the freshmen, I've done that for the sophomores, I've done that for the juniors, and I've done that for the seniors. I took each person's score, subtracted the subgroup average for that unique group, and now I've squared them all. And as a last step for my sums of squares within, I just add all of these squares to get the sums of squares within the groups, because I looked within each group. And that's exactly what I've done here. I've taken all these squares and I've added them all up for us. I added all these up, and then I added all these up, and then I added all these up, and then I added all these up. Added all those up, and the total sums of squares within is 38. So I put that on my table, 38. Now, hooray! I can complete this ANOVA table, this source table. If I wanted to figure out the total sums of squares, I could just add these two. And I get 81 plus 38 is, looks like that's 9. And 8 plus 3 is 11, so 119. Right, 81 plus 38 looks like it's 119. And then I take 3 plus 16, and then I get 19. And then I take, to get my mean square between, I take 81 and I divide by 3. So I take the sums of squares between and I divide by the degrees of freedom between. And 81 divided by 3 is 27. And now to get my mean square within, I take 38 and I divide by 16. And I get 2.375. 38 divided by 16 is 2.375. And as a last step to get my F statistic, I'm going to take 27 and divide by 2.375. And I get 11.368. That is my inferential F statistic. And then I would compare that to a critical value. And then if what I calculated was bigger than the critical value, then I reject that null hypothesis and say somewhere among these groups, 2 of them are different from each other, at least. One pair, there is a statistically significant mean difference. I don't know which pairs yet. Could be all, could be one, but at least one. Because this F, if it's bigger than the critical value, I reject that null hypothesis that all the groups are equal. And if all the groups are not equal, well, then at least one group is different than one other group. All right, that's it for this time. We're going to have a whole second lecture on ANOVA where I'm going to run through another ANOVA example where we'll actually we'll learn to look up the critical values together in table A3. And then we'll learn about these things called follow-up tests, right? So we're going to do a whole nother example where we actually look up the critical value and make a decision. And so I'll see you next time.